convergence hold on larger sets that might grow with n? Okay, so that's the first question I want to ask is, fixing x and t in a compact set and letting n grow to infinity is nice, but you really would like to see that the asymptotics that we're computing later holds on a region that where there's still n solitons. Okay, and so that's the first question. And the second question is, hey, if I go back to this original n soliton problem, what is the effective support? Okay, how large? What's the spread of the location of the solitons in this particular setting? So all right. So on this slide, I'm trying to start describing the answer to the first question. Okay, so on this slide, I have the A problem and the A infinity problem. And in order to prove convergence, you need to control actually this quantity here. So that's maybe the question you were asking. You know, I have to control A minus inverse 0, 1, 1, 0, A minus inverse times this is what will hopefully give us some control, this difference between the integral and the sum. Okay, now if x is growing, then this is not bounded. This actually grows exponentially in x. And this prefactor, if x is growing, is also large. So you wind up having to control this quantity, where this e to the c times x, that's exactly the contribution from the solution A infinity and from this exponential. And so now this is the thing to control. I would like to ensure that this quantity, e to the c times x times 1 over n squared, goes to 0. So that means x has got to basically, it could be as large as negative log n. Okay, so fine. So this is what we have. We have uniform convergence on some set like this, and n can grow, right? So it's just as n grows. So sort of the growth rate where we still have convergence is log n. Okay. Say again? Well, it's a uniform convergence on this set. Yeah, and for positive infinity, yeah. For x going to positive infinity, all of the exponentials are decaying at some fixed rate. So that side's actually easy. It's the other side that's hard. Okay.
The constant c in the exponent is negative.
No, it's positive. That c is positive. Yeah. Yeah. So
And that's not related.
Sorry. There should be an absolute value on the x. There's I don't want x is large and negative. This should be a large quantity. That's the point. So if I've got a sign mistake, let me think about it for a second. Yeah. There should be an absolute value on the x. And then it's no problem. If x is big and positive, okay. This was designed, and it probably, let me think about it for a second. Yeah, that inequality is not right. The inequality that I want is c e to the negative some positive number times the absolute value of x, and I'm only worrying about x less than -1. Okay, so it's this thing over n squared should be less than epsilon, and then you move the n squared over, and then hopefully this winds up being the correct inequality. Okay. I still have a negative sign mistake.
Maybe you don't need the other value. I don't think you need that. So then it matters which sign of anything. Yeah.
So you want me to put this without this? Yeah. Agreed. Yeah. I mean, I'm only worrying about x negative, right? For x positive, everything is decaying. So this was yeah. So there's a negative sign missing from right here. Okay. So the punchline is you have uniform convergence on this set. Okay, and the set is growing in the direction of negative infinity. It's just easy to establish convergence on all positive x, basically. Okay. Sorry for that mix-up. Is that okay? All right. So the other question that I posed was, what's the effective support of this n soliton configuration if n is large? And so so this is maybe connected to the question Mark asked. If x is large and positive, then all of these exponentials are decaying, right? So kj's are positive numbers, and that gives me exponential decay. So I can show very easily that there is a constant c, so that if all x bigger than c plus log 1 over epsilon, the solution is less than epsilon. That's the n soliton solution is less than epsilon, okay? Now, if x is large and negative, we have to actually, none of this, it's terrible. This is now a large positive exponential. It's just not under any control. So again, we use trick number 7, which is to reverse triangularity. And so up there is the definition of M1, in which I flipped the triangularity at all of these n poles, okay? And then down here is the new residue conditions. I've only written them down now at the poles in the upper half plane because the poles at the lower half plane follow by symmetry. If you compare this residue to this one, you see the signs have changed in the exponential. That's good. But then we pick up a Blaschke factor for each of the poles that we reverse triangularity. So it's a product where j runs from 1 to n of this kl plus kj over kl minus kj, and L is I'm looking at the residue at ikl, okay? So this is actually, this quantity, this product is exponentially large in n, okay? So, so I've rewritten the residue conditions, okay? And in order, I'm looking at the situation that x is very large and negative, and I would like this quantity, which is the residue, to be less than epsilon for all L. So unraveling that means that x is less than this sum of logs, this logarithm of n that came from this n here, and a log of epsilon. Okay, that's actually the inequality, but that's supposed to be true for all L, and that you can then sort of optimize that by just defining some capital L to be the max of this integral. And what you wind up learning is the support is contained within a set, the left-hand endpoint of which is negative n times capital L minus log n plus log epsilon, and the right-hand side of this interval is log of 1 over epsilon plus c, and L is the maximum of this integrand, of this integral, okay? So the effective support is an interval of length n, plus a little bit, depending on epsilon, okay? So now some interesting problems. I promised I'd mention some interesting problems. So can you choose these residue conditions, these R's, and also the distribution of kappa j's to minimize this support, right? Is n actually the right scaling, or is there a way to choose them so they're really closer together as n grows? And I learned from Gennady and Giacomo and Thibault that they kind of know which one it is. It should be the distribution of eigenvalues that comes from a square well in the semi-classical limit, right? And that's like a fantastic problem to describe that. It's like, how much can you engineer these gases? And that's something which Gennady and his crew are just the masters of, okay? So here's another one. The effective support is order n, and I've shown you convergence to the soliton gas potential on an interval of size log n. So there's a huge region where there's interesting phenomena. So that's the interesting quest. As n grows, look at the n soliton solution and try to study interesting phenomena for x in this window. And there ought to be some kind of an edge of the convergence to the elliptic background wave. There ought to be a soliton edge. There should be some transitions. Probably a lot of the existing asymptotic analysis can be just ported over and reinterpreted in this setting. But it's the finite n soliton behavior as n grows type of problems. Okay. So I got to, maybe there's 10 minutes left. So I think I'll finish on time actually. Okay, but the last thing I wanted to talk about is a way to introduce randomness into this particular collection of soliton configurations. Okay, so what if we took the pole locations to be random? Okay, so here's one way to do it. There's many ways to do it, I know, but here's one way to do it, which is particularly useful because there's probabilistic results, you know, all over the place in this setting. So here's an example: Laguerre-Wishart distribution of random matrices. So I'll define it very quickly. Usually I have a bunch of slides that walk people through what is a random matrix at this point, but I'm not going to do that. So just imagine you have an n times m matrix. So it's not square, X, and you fill it with IID entries. They're all standard Gaussian normals. Okay. Then, okay, I'm going to let m, you know, I guess that's the width of the matrix, be larger than n. So this limit is alpha, and alpha, okay, it's actually going to be bigger than 1. Okay, not even equal, bigger than 1. Then you construct the eigenvalues of the matrix X transpose X divided by n. Okay, so they're all positive because positive definite matrix has positive eigenvalues. In random matrix theory, it's one of the pushes, one of the interests has always been in this kind, in the eigenvalue statistics. So you open any paper in random matrix, so you'll see this sum. Lambda j's are the eigenvalues, not kappa j's, but lambda j's. And linear statistics, they're called. Fundamental statistical quantity is the linear statistic, and the lambda j's are not independent. That's the critical difference in random matrix theory, is that the eigenvalues are not independent quantities. It's sometimes the matrix entries that are independent, sometimes not even those are independent quantities. But there's a lot known about these linear statistics because of a different amazing connection to integrability that I just won't talk about, okay? But why is that useful? That's useful because you remember trick number 3 was to remove all the poles. And that's the Riemann-Hilbert problem that emerges after you remove all the poles. And what you have sitting here is a sum of a function of kappa j evaluated at all of the kappa j's. So it's exactly the jump entry there is a linear statistic, exactly as it would be from random matrix theory. So that's why this is a useful version of it's a useful way to introduce randomness. Okay. Then here's the kind of results that are old school results in the theory of random matrices. It's called weak convergence in probability. You got to put on your, I'm thinking like a probabilist hat, and I'll avoid the jokes that are necessary at this point, because I think there's maybe no probabilists in the audience. Okay, so turns out there's a limiting density of these eigenvalues, and that's referred to as d sigma. In this case, it's written right here. D sigma is this density function here times dx. So it's beautiful distribution of eigenvalues. It vanishes like a square root at both endpoints. And the linear statistic, as long as f is a nice continuous function, this sum converges to this integral. And this statement is a probabilistic version of that statement. The probability that this sum minus the integral is bigger than epsilon, that goes to 0. Okay, so you can think morally, oh, I should be able to replace the sum by the integral, and making a small error. Okay, so that leads you, okay, and yeah, in terms of the jump matrix up there, that's what you have, that this expectation should converge to this integral, the integral of r times d sigma over z minus s. So d sigma is okay, right? It's just this density function times d. So it should be ds over there. Is it? D sigma of s, yeah, okay, good. So that leads you to this model problem, A0, where I've replaced the sum by the integral. Just replaced it. So there's no comparison yet. You have no idea if this has anything to do with the finite n random solution to the Riemann-Hilbert problem. Just replace it with this one. But that is exactly a soliton gas problem, right? There's no more randomness in this, but it's exactly of the form of the Riemann-Hilbert problem that Manuela spoke about. And so you can even collapse it back down to these two intervals in the upper half plane and lower half plane. And that's the effective jump entry that we have to deal with, okay? So if you were keeping score, it vanishes like a square root at both endpoints. That means that our large X asymptotics is actually, it's not decaying slowly to the elliptic wave, it's decaying exponentially towards the elliptic wave. Okay. Okay, so this Riemann-Hilbert problem determines some quantity u0 of x and t, which is probably the average of the potential. Okay, and so very recently, Manuela and I worked out the details of these three statements, which are probabilistic statements. So I'm describing them here. We're still in the process of writing it up, but these are the statements. The first one is the probability that the n soliton solution minus this average is bigger than epsilon. That probability converges to 0 as n goes to infinity. Okay.
Uniform overall x, overall t, or are there?
This is in compact x and t. Yeah, compact x and t. Certainly, it's not something different is happening for large x or large t. Yeah. Second statement is that it's funny. This looks like it's some statement that says the average converges, but actually it's harder to prove that the average converges. And so that's the next statement, is that the average of the n soliton solution does converge as n goes to infinity to this u0 of x and t. And the third statement is kind of our favorite statement. You take the n soliton solution, subtract this average and square it, so it's the variance, goes to 0. So all the fluctuations are shrinking to 0 as n goes to infinity. So that provides sort of analytical justification on compact sets of the statement that these regular soliton gases, as we call them, are actually representative of random soliton gases. Okay. Now I promised that I'd finish on time and that I would have just some discussion of open directions, so there's still some time for that. So here's a few interesting problems that are connected to this one way of introducing randomness with the hopes of analysis. Okay, so what's the rate at which the variance converges to 0? Right? I said this statement, it goes to 0. What's its rate? That's a much more challenging problem, and even on compact x and t, that one seems to be but maybe it's doable because of the strong connection to random matrix theory. And then after you compute that rate, then of course we're thinking like probabilists, right? So that means we're looking for the central limit theorem. And that means you take this random quantity, subtract off its average, divide by the sigma, okay? Then ask, does that have a limit theorem? Does that converge to a Gaussian or something else? It probably converges to a Gaussian. That'd be crazy if it didn't converge to a Gaussian, but that's sort of the next kind of question that you might ask. Okay, and so those are the two statements from the previous slide, two interesting questions from the previous slide. Then, you remember I was describing the effective support, right? But that was for a pretty regular configuration in which the integral converged, the sum of logarithmic corrections converges to, oh, I think I have a slide about that. Yeah. Okay, so remember, it was this quantity. In order to control that, that forced how large x was, but that's a pretty regular configuration. So what does it look like in the random case? Okay. That's okay. So is there a difference if you take random data, or is it just that it's sloshing about? Can you be precise about the edge and study that random variable? Okay. It'd be cool if it was some random matrix thing like Tracy-Whittem distribution. It could very well be, because the edge is probably associated with the largest eigenvalue, right? Because the fastest one is the largest one for KDV. Okay, so but then what about the edge of this convergence to the elliptic region? How does that survive the randomness or get destroyed by randomness? And in general, if you all of the convergence results, are essentially on controlled sets in X. X might grow like log of n. How does that work? Sorry, X might grow like negative log of n. How does that work if you have randomness? And what about transition phenomena? How does all of that play with randomness? Okay, and that's the end. So thank you all for your attention. Sorry again for the complications.
Okay, thanks for your wonderful talk. Are there questions?
Nice talk. Enjoyed that. I was thinking that for 50 years, a goal has been to be able to communicate with solitons or breathers in fiber optics cables. And it has not been ever successful relative to competition with linear systems and so on. But it seems like maybe you've got some structure here that and some mathematics that would allow people to do that kind of thing in fiber optics. I don't know if you've thought about that. That's a first comment. The second comment is that we ran into this probability problem for KDV and found that using the Itzmat-Veya formula, okay, that if you could have a good statement about what the probability density of a theta function is, which for ocean waves we were able to do, and then take the second derivative of the logarithm of it, we could get the actual probability density of the waves in the soliton limit. And this, by the way, fit data taken from Kurtuk Sound off of North Carolina many years ago, 2002, fit the probability density for the soliton part of the spectrum. So you might get some ideas from some of that work.
Okay, okay. I haven't thought about the communications problem. I thought about it a little bit many years ago with Greg Forrest, but I haven't thought about it recently at all.
Okay.
So, yeah. And yeah, I'll take a look. Thank you for that. Yeah, I guess I should say that there's another direction where you want to study soliton castles, so randomness and solitons, but from the point of view of high genus theta functions that that Gennady and Alexander Tovbis and others are developing. So it's in that same universe.
Yeah, nice talk. I have a question and comment. First, let me start a little background. So we're doing a lot of, I think, somewhat related things in free surface hydrodynamics when we do analytical continuation outside of fluid, when we typically have branch cut and we approximate by poles. But what happens, except your last part of your talk, you mostly work with uniform placement of poles.
Yeah.
Well, and as a result, you have 1/n² convergence.
Yeah.
But if you place poles more clever, you can easily get exponential convergence in n. So it's like analog of, low order finite differences versus spectral method for analytic functions. So this is, I think, so you never explored this direction. You can really, extremely speed up convergence if you think about some numerical applications. Have you ever thought about this?
No, but that's a great idea. I mean, I think Bob and Manuela were telling me with,
Because it's like
trapezoidal approximation is really good if things decay exponentially at the edges. It's actually almost exponentially convergent in that case.
But you're showing 1/n², right?
Yeah, because I wasn't assuming, I don't know where I'm clicking the buttons as though I know what I'm doing, but I don't really know what I'm doing. Yeah, I'm assuming, this is the wrong one, wait, back. That one, yeah. So there I'm assuming that R doesn't vanish at the endpoints. You see that?
Mm-hmm.
And then you have this explicit connection.
Yeah. But if you bunch again, you can have exponential convergence easily.
That would give a larger set on which convergence holds. That's the immediate result of that. You'd have a larger set on which convergence holds. But can I just quickly say, notice, it would be also interesting in this case to compute the contribution from this 1/n term. It's like a tiny pole at the edge of the band, and that's sort of another crazy problem to look at.
Yeah, of course. Yeah, I mean, we kind of routinely do this in our applications too, with full Euler dynamics. Yeah, but yeah, I think it would be very efficient potentially.
Thank you.
Further question?
Ken, thanks very much for the beautiful talk. So a question on when you introduced the Laguerre-Vizard distribution. So basically introduce a vector of normally distributed variables, construct the correlation matrix, and identify the eigenvalues with the poles. So what is the interpretation of the original vector in connection to the soliton problem?
You mean the eigenvectors?
The vector of the normally distributed variables.
Oh.
Yeah.
Okay, the x's.
The x's, yes.
Yeah. So. Yeah, so here's this may not answer your question, Antonio, but it's like random matrix theory. You start with some collection of independent random variables, and you form the matrix, and then you say, I'm going to study the eigenvalues. Okay, and those are madly correlated, and you just get lucky that you can compute the change of variables from matrix entries to eigenvalues and eigenvectors and just wipe away the eigenvector information. So you lose all of that content. Okay, so there's a very weak connection between what the x's, the entries of x are, and the eigenvalues in the sense of analysis. Okay, is that what you're asking? Or are you asking how the x's are connected to the Riemann-Hilbert problem?
No, I was wondering if you define you start from a soliton gas problem where you have a number of random variables, and you arrange that in some random matrix context, and then the eigenvalues will have an interpretation in connection to the original matrix ensemble. So I was just wondering whether the original matrix ensemble has an interpretation in terms of configuration of macroscopic configurations of your system, as it happens in quantum field theory and other contexts.
So we really think of it as artificial. I use the random matrix model to select eigenvalues, and I use those as locations of the poles. And it does induce a measure on the potential, right? But it's not natural. It's like the starting point is the distribution of eigenvalues from random matrix theory and just interpreting it as distribution of poles. Okay.
Thank you.
Yeah, I'm not sure who was first.
Hi, Ken. Thanks a lot for the talk. So in one of your last slides, you mentioned, I mean, when you introduced probabilistic kind of randomized soliton gas, which I think it should be. So yeah, lower, maybe where you introduce
where we introduce
variances and
the variance. So that's near the okay, that there.
Yeah, and you show that the variance of this random process basically it goes to zero when the number solitons goes to infinity. But this would imply, if I'm not mistaken, that the process almost surely is a constant.
Well, U0 is not a constant.
U0 is not a constant.
No, U0 is one of these elliptic. So it's
yes, yeah, okay.
So this is not this is actually an example of a regular soliton gas. So it has the following nature. So it's x, if you let x go to negative infinity, then it's an elliptic wave. If you let x go to plus infinity, it's decaying. And then if you study the long time behavior, there is this modulated genus 1 region and then a non-modulating genus 1 region and a quiescent region.
Well, great, thank you. So what would, I mean, could you just describe qualitatively what do you think the typical realization of this gas would be?
Yeah, so I don't have the mathematical answer from this. If I had this, I would say that the U minus U naught would be equal to some random variable times this variance, right? So I need to know how fast this decays in order to say U equals U naught plus something fairly explicit X and T dependent random variable, right? That's sort of one of the reasons why, is there a limit theorem for this is a critical question, okay? Is it Gaussian?
Okay.
I would guess that, I mean, that may be a question I can ask you. What do you think it's sort of white noise in this limit? Is the fluctuations going to be
Yeah, so I mean, I think it will be kind of it's deterministic as well, it will be kind of blurry, something like this.
Yeah, okay, but what kind of blur? I mean,
Yeah.
You're saying, so U, which is the random thing, is going to be U naught plus some sigma n, which is going to go to 0 at some rate, times some random variable, I'll call it C with a tilde on top to make it even more weird. So what is this this is going to depend upon n, and what is it, and is there a scaling limit for it?
Yeah.
Right. So this is the blurriness, right? And characterizing this is like, that would be a wonderful thing to be able to say precisely, okay, this is in the limit becomes a Gaussian, or this in the limit is described by random matrix theory.
Okay, thank you.
So U upper 0 is, so I had this problem where the series has random coefficients, the kappa j's or the kj's are random. Okay. And then if I replace that series at the top by its average, so replace this by its average, that is a different Riemann-Hilbert problem, which is called A0. It determines a potential, which is U0. Okay, so U0 is the solution to the KdV equation corresponding to this Riemann-Hilbert problem, to the average of the poles.
Okay, so I think we defer all further questions to the coffee break. So for the present participants, there is a coffee break, and for the online ones, I'm sorry. you have to get your coffee yourself. So let's thank our speaker again, and we'll reconvene at 10:30.